In this course, 201, and also in its follow-up, 202, we mainly deal with linear circuits. Okay, so therefore, the tools and methods that we already developed and we will have developed in the future are mainly helpful to analyze and design linear circuits. So, in general, if you have a nonlinear circuit, then you have to resort to some other methods. But there are a few important exceptions to that, and today we will talk about one of those exceptions. Okay? The case that we will deal with today is a nonlinear circuit. It's resistive. Okay, the circuit is resistive, and the nonlinearity of the circuit is due only to a single nonlinear component, a nonlinear resistor. Okay, that's one of our assumptions, and the other assumption is that the sources throughout the circuit are either constant or they're almost constant. Okay. So in that case, our linear methods will be sufficient to obtain a reasonable answer. Okay. So consider the following scenario, okay, where we have a constant voltage source, providing voltage E. We have an LTI resistor with resistance R, and here we have a nonlinear component, a nonlinear resistor. Okay. Nonlinear resistor. And when the circuit runs, there will be a voltage drop across our nonlinear component, and there will be a current passing through it. And the aim is figuring out what's V0 and I0, so-called operating point. Now, for that, what we require is, of course, we need to know something about this nonlinear resistor. In other words, we need to know its terminal equations. Okay. So, the IV characteristics of the nonlinear element is supposed to be known. Okay. Plus minus V. This is I, and the relation between the current and voltage for the nonlinear resistor, nonlinear component, is known and described by some mapping, okay, G. Or sometimes voltage is expressed in terms of current. Okay. V equals some function of the current, let's say. Now, what can be said about V0 and I0, or what's the equation to be satisfied by V0 and I0? It directly follows from KVL. Okay. Now, KVL says that voltage, sum of voltages in this loop, and there's a single loop in this very simple topology, must sum to 0. Okay. So we have E equals this voltage, R times I0, plus the voltage drop across the terminals of the nonlinear resistor. And that, if you replace the current by its expression in terms of voltage, you have an equation only in terms of voltage. Okay. Or, if you use this relation, V equals some function of I, then we have E equals R I0 plus F of I0. Now, the problem is, solve for the voltage and current of the nonlinear resistor. That is, find the pair I0, V0. Okay. There are two possible solutions, or two possible approaches to this problem. One of them, let's call it solution 1, is as follows. It's called algebraic solution. Okay. Solve the equation RGV0 plus V0 equals E. E equals RGV0 plus V0 for the only unknown, V0. In this equation, we assume that E is known, R is known, this function G is known. Therefore, there's only one unknown, and that's V0, the voltage of the nonlinear resistor. And then we can attempt to solve that equation, which has just a single unknown. And once that V0 is figured out, we can use the relation between current and voltage to figure out I0. Okay, once V0 is found, plug in to here, okay, and G of V0 gives you I0. Then compare our operating point I0 V0 equals G of V0 and V0. This is the solution. Okay. Now this approach assumes that this function G, which characterizes the IB relation of the nonlinear resistor, is known. Okay. Sometimes it's not known as a function, but G is described as a collection of points, let's say, or we know what G is in a graphical way. In that case, we have to use the graphical approach to figure out the operating point. So what I mean is the following. Sometimes the current voltage relation of the nonlinear component is available only as a measured curve. Which, for instance, you obtain in the lab by performing a voltage sweep. Okay. In that case, we have to solve the problem in a graphical way. That's called graphical solution. In graphical solution, what we do is we sketch out the constraints on this pair, operating point I0, V0, and intersection of those constraints should give us the answer. Okay, so we have two constraints. Okay, two conditions that must be satisfied by the current and voltage of the nonlinear component. On the set of possible I0, V0 pairs. Okay. Okay. The first constraint, constraint 1, is due to the circuit or the topology that the nonlinear component is subject to. Remember that we have the voltage source and linear resistor and our nonlinear resistor. They all make a loop. Okay? So by KVL and the terminal equation of the resistor, we have Ri plus V minus E equals 0. Okay, so this is the voltage of the nonlinear, linear resistor. Okay, R times I is the voltage of the linear resistor plus voltage of the nonlinear resistor, and that sum must equal the voltage provided by the voltage source. Okay, so therefore we have Ri plus V minus E equals 0. So this constraint can be called the external constraint. There's also the internal constraint, or a constraint that can be called internal, and that has to do with the IV characteristics of the nonlinear component. Okay, so that constraint is characterized or represented by the function g that we have used here. And the second constraint, or the internal constraint, is I equals GB, or I minus GB equals 0. Here I and V are the currents and the current and voltage of the nonlinear resistor. Okay. So this is due to circuit that the nonlinear resistor is connected to, and this is due to nonlinear resistor itself. Okay. So this must hold regardless of the circuit that the nonlinear component is connected to. Okay. And now any solution candidate I0, V0 must satisfy these two constraints simultaneously. Must simultaneously satisfy both of these constraints. Okay. So let's try to visualize how those constraints look like on the IV plane. Okay, so we have the current for the vertical axis and voltage for the horizontal axis. Suppose that the solution is somewhere in the first quadrant. Okay, so we don't have to worry about the other parts of the plane. Okay, so this is the origin. And so we have the first constraint, Ri plus V equals the constant E. Okay, E is V. E is the voltage provided by the battery or the voltage source. So this describes a line, and that slope depends only on the resistance of the linear resistor. Okay. And then if you draw that line, this is what you have. Something like that. So this is the point where the current is 0. Okay. Now we're talking about the first constraint. If you let the current equal 0, so therefore what you have is V equals E. Therefore this constraint cuts the horizontal axis at the voltage E. And as for the other intersection with the other axis, this time the voltage is 0. If you let V equals 0, so what you have is Ri equals E. Therefore I, the current, when the voltage is 0, is E over R. So this point here is E over R. Okay. Okay, and here we have, therefore, all the points, okay, on that line satisfy the first constraint. Clearly, that's not the only constraint. We also have the constraint due to determining equation of the nonlinear resistor. So if, suppose it looks like this, something like that, and this is the curve I equals G, and this curve describes the set of points that satisfy the second constraint. Okay. Now, since in a running circuit, the nonlinear resistor or the current voltage pair for the nonlinear resistor should satisfy both of those constraints. Clearly, from the graphical point of view, the operating point or the solution is where those two curves intersect. And in this case, in our picture, it corresponds to this point. So the voltage of this point is the operating voltage, and the current corresponding to this intersection, I0, is the operating current. Okay. And this is called operating point. Now this is I equals GB, and this is the line due to the first constraint, that's due to circuit, and that line is a special name. It's called the load line. This is called load line. Ri plus V equals E. And this is I equals GB curve, which can be called the terminal equation curve, if you will. Okay, so that's the graphical way to look at the problem. Now, in this nice picture, we have only a single intersection. Sometimes there is no intersection, meaning that there will be no solution to the problem. Sometimes there may be more than one intersecting points. In that case, each of those points is a possibility as a solution. Okay. Now, let's talk about an actual example. And by the first method, the algebraic method, let us attempt to figure out the answer. This is our simple topology, where here we have a constant source, constant voltage source, an LTI resistor with resistance R, and this is our nonlinear component, nonlinear resistor with voltage and current given as such. And here is the terminal equation, or the terminal characteristics, or the ID characteristics for the nonlinear resistor. It's given in a piecewise fashion. Okay. The current depends, or the current is proportional to the square of the voltage. Not everywhere, but when the voltage is positive. Okay. So this is the relation I equals 0.03 V squared whenever the voltage is positive or zero. When the voltage is negative across the terminals of the nonlinear component, it behaves like an open circuit. Therefore, the current is zero elsewhere for V less than zero. Okay. So that's the terminal equation. As for the values for E and R, we're given E equals 10 volts and R, the resistance, is 100 ohms. Okay. Now, for this circuit, for these values and that terminal equation, let's figure out voltage and current of the nonlinear resistor. So find the so-called operating point. Here goes the solution. V volts by in amps. This is the origin. Okay, the load line is this straight line with negative slope, and this point is E over R. E 10 R 100. Therefore, this is 1 over 10. Okay, this point 1 over 10 amps. As for this point, it's directly E. E is given to be 10 volts, therefore this here is 10 volts. Okay, so whatever the operating point is, it must be somewhere on this line, which we call the load line. And then, how about the IV curve? When V is negative, the current, the component behaves like an open circuit and the current is zero. So that means all these points, all these voltages for which the current is zero is a possible operating point. Okay, well, disregarding the load line for now. And then, when the voltage becomes positive, the current is no longer zero and starts to increase in this quadratic fashion. Okay, the increase will be slow for low values, for small values of V, but eventually, because of this V squared term, it gets larger and larger. Okay, in polynomial way. Okay, something like that. And then the intersection clearly is in the first quadrant somewhere, and we're looking for this point, which we call operating point. This is V0 and this is I0. So all we have to do is write down what we're given, okay, and then solve the problem algebraically. Okay, so by KVL, we have 0 equals Ri plus V minus E. Okay. So we're summing all these three voltages. This plus minus this voltage is R times I. This voltage is V. And then this voltage plus minus is minus E. Okay. Ri plus V minus E equals 0. So that's the equation that describes the load line. And R is given to be 100 ohms and E is given to be 10 volts, therefore this equation becomes 100I plus V minus 10 equals 0. Okay. So let's call this equation number 1. Now, let's figure out, therefore, using the Therorem equation, the operating point. Now, there are two possibilities from what's given. It's either V is negative and V is positive, because the relation is given, the current voltage relation is given in this piecewise fashion. Okay, so let's consider first this negative V and figure out if there exists a corresponding current to it. And then in this second part, we let voltage to be positive, and then the current in that case is this. And using this expression for the current, we will try to solve that equation. And then that will give us, if it exists, some voltage. So case V negative. Okay, so assume that V is negative, the voltage of the nonlinear component. In that case, the component behaves like an open circuit, and the current is 0. Then you plug in I equals 0 in the load line equation number 1. If you do that, this term disappears and you have V minus 10 equals 0. Therefore, V must be 10. Okay? So 1 implies that V equals 10 volts. But that violates the assumption that we made in the beginning, which is V is negative. Therefore, this case, V negative, does not produce any possible solution. Okay. But V was negative, hence no solution exists for which voltage is negative. So now consider the other possibility where V is 0 or positive, okay, where V is not negative. When V is not negative, we're talking about this case, the current is, in terms of voltage, 3/100 V squared. Okay. I equals 300 V squared. So what we're going to do is we're going to replace this I here in the load line equation with this expression and obtain quadratic equation in terms of V, which would have two roots. And by looking at the root locations, we will try to see whether either of them satisfies this assumption. If it does, then that would be the solution. Okay. So, load line equation 1 implies 0 equals 100 times I is here 3 over 100 V squared plus V minus 10. So that's 3 V squared plus V minus 10. And this can be factored out as 3V minus 5 times V plus 2. Okay. So once you write the right-hand side as 3V minus 5 times V plus 2, it's clear what the roots are. We have two roots, both real. One of them at 5 over 3, the other is at minus 2. Okay? So this equation tells us there are two possibilities, or there seem to be two possibilities. One of them 5 over 3 volts, the other is minus 2 volts. V equals 5 over 3 volts or minus 2 volts. But only one of those solutions is the actual solution, because one of them violates the assumption that we started with, and that assumption was V was positive. Okay? Therefore, this is not possible, okay? Because V is non-negative. And that leaves us with the only possibility, which is V equals 5 over 3 volts. Okay? This V satisfies. Okay, this V and the corresponding current satisfies not only the load line equation but also terminal equation. So since both constraints are respected, that's a valid answer. Okay. So we solve the circuit. Let's put down our final answer on the board. So finally, the operating point must have the voltage V0 equals 5 over 3 volts. And then the current can be computed either using the using the load line or the terminal equation. They must both give the same answer. So let's use the terminal equation. 3 over 100 V0 squared, which is 1 over 12 amps. Therefore, operating point or the current voltage pair of the nonlinear resistor for the given circuit is I0 V0 equals 1 over 12 amps for the current and 5 over 3 volts for the voltage. Okay. Now, we have solved a circuit with a single nonlinear resistor, and some may say that, okay, but that was a very simple topology, that was a very simple circuit. We only had one loop, and in that loop we had just 3 components. Even though it's a very simple topology, it's still, what we did here is still quite general, because since we are assuming that the nonlinear component is the only nonlinear element in this circuit, therefore the circuit or the one port that is connected to must be linear. And whenever that's the case, it can always be represented by its Thevenin equivalent. And once that linear one port is replaced by its Thevenin equivalent circuit, we have the topology that we work with. Okay. And also, we can use the substitution theorem to deal with the more general situation. So let's quickly remember the substitution theorem, and we will apply it together with Thevenin equivalent circuit method to solve a more general problem. Let us have a circuit as follows. Okay, you let's call this component gamma, the one port. And here we call the voltage across the terminals of this component Vx, and its current we're calling it Ix of t. And gamma is just an arbitrary resistive component. It doesn't even have to be resistive, just an arbitrary component. Now then, by substitution theorem, you can replace that component by a voltage source, independent voltage source that provides voltage that equals Vx of t, or you can replace that component by a current source that provides current that equals Ix of t, and within n, everything will still be the same. Okay, in other words, an observer sitting inside n will not be able to tell the difference. That's the beauty of substitution theorem. Okay. Then, by substitution theorem, that was one of the tools that we have seen earlier in the course, we can make the following substitutions. We can either replace the component by a current source. Okay, and the direction of the current source must be same as the direction of the current that's used here, and the current of the current source must equal the current that's computed or measured in this first original case. Okay. Or we can use the other possibility. We can replace this component with a voltage source, independent voltage source. Okay. And the voltage provided by that voltage source equals the voltage that's measured or computed here, Vx of t. Vx of t. I know that the polarity here plus minus and the polarity here plus minus, they must match with one another. Okay, we could either do this or that substitution without affecting any branch current or voltage inside. Branch or voltage. Within one port N. Okay. Now, using those two powerful tools, namely the substitution theorem and Thevenin or Norton equivalent circuit, we will now solve a nonlinear circuit that contains a single nonlinear element. This is our circuit. We have 4 LTI resistors and 1 nonlinear resistor, and the whole circuit is driven by a constant voltage source that provides 7.2 volts. Okay, this is given to be 8 ohms, 6 ohms, 4 ohms, 12 ohms, and this is our nonlinear resistor, whose current and voltage are denoted by I, R, and VR. Okay, and the relation between those two variables, the current and the voltage, or the IV characteristic of the nonlinear component, is given as 0.25 VR squared for positive voltages and 0 elsewhere. That is, for negative voltage, this component behaves like an open circuit. Okay. Now, in this circuit, we're not asked for the operating point for the nonlinear component, but we're asked for some other variable in the circuit. Okay? Namely, we're asked for the voltage drop across the terminals of 12 ohm resistor. The question is, find the voltage V. Okay. Now, what we're going to do is, we're going to divide the problem into simple sub-problems, and then in a step-by-step fashion, we will solve the overall problem. Okay. First, what we're going to do, the aim is to find the operating point. Okay. How we can find the operating point? Okay. Remember that it was very easy to find the operating point when we had a very simple topology. A constant voltage source, an LTI resistor, and our nonlinear resistor, okay, connected in series, in a loop. So, therefore the first step would be to convert this circuit to that topology. And that we can do because the circuit that's seen by the nonlinear component, or the one port that's seen by the nonlinear component, is completely linear. Okay, it's LTI. Therefore, it will have a Thevenin equivalent representation. So just take this out and leave this as a one port, LTI one port. Figure out the Thevenin equivalent representation for that LTI one port, and then replace this not so simple topology with that simpler Thevenin equivalent circuit topology. In that case, we have the topology that we worked with in the previous example. A voltage source, an LTI resistor, and a nonlinear resistor. And then, using that very simple circuit, we obtain the equation to be satisfied by the voltage, let's say. And then from that equation, we obtain the voltage. Using the terminal equation, we figure out the current. And then we have the operating point. Okay, the voltage and the current in this scenario. If you were asked either for the current or the voltage, then at that point you would have been done. But we're not asked for this current or voltage, but we're asked for some other variable within the circuit. So therefore we have to go back to the original configuration. Now, in that case, what we do is, at that point we will have known this voltage or that current, and what can be done is the following. Just replace this with a voltage source that provides voltage that equals operating voltage, operating point voltage, or replace this by a current source that provides current that equals operating point current. If you, after that substitution, this is replaced by an independent source, and this circuit becomes completely LTI. Okay, it's an LTI resistive circuit, and then apply your favorite method, mesh analysis or current node analysis, to figure out the variable that you're asked for. Okay. So let's now apply that strategy and obtain the voltage. Okay. So, step 1. Obtain the Thevenin equivalent circuit seen by the nonlinear resistor. Okay. That is, take this guy out and leave this circuit as one port. A, B. This is what remains when you take this nonlinear resistor out. It's 8 ohms, 6 ohms, 4 ohms, 12 ohms, and this is 7.2 volts. Okay. This LTI one port will have a Thevenin equivalent circuit. We have seen many examples. So it has the following structure. Here we have a constant voltage source because the source here within this one port is constant, and here we have an LTI resistor. So the resistance of this resistor is called the Thevenin resistance of this one port, and this voltage provided by this independent voltage source is the Thevenin voltage of this one port. What was Thevenin voltage? It was the open circuit voltage, okay, that appears across these nodes A and B. Okay, so if you let this pair of terminals open circuited and figure out the voltage drop, okay, or the between these two nodes, that happens to be 6 volts, and 6 volts is the Thevenin voltage. Okay? And then you can short those two nodes and figure out the short circuit current in that direction from A to B, and that will be your Norton current. Thevenin voltage divided by Norton current, and Norton current turns out to be 1.5 in this case, gives you your Thevenin resistance, which is 6 over 1.54 ohms. Another way to compute Thevenin resistance, remember, was kill all the sources inside the one port. In this case, there's only one independent source, and killing it means you replace it by a short circuit. Okay. So you replace it by a short circuit, then 6 and 12, they become parallel, and the equivalent resistance is 4, and then that 4 and this 4 become series, so the equivalent thing is 8 ohms, and then that 8 ohm and this 8 ohm are parallel. The equivalent resistance is 4, which is your Thevenin resistance. Okay, so that was step 1. Then step 2 is, now we can replace this circuit with its Thevenin equivalent representation, and it's much easier to work with that new circuit. Obtain the operating point using the Thevenin equivalent circuit. Okay, so this is the Thevenin circuit, 6 volts, 4 ohms, and we have the nonlinear resistor. plus minus VR, and here is the current IR. Okay? Using this circuit plus the thermal equation given for the nonlinear component, we will now figure out the operating point, IR and VR. Okay. So, by KVL we have 4 IR, okay, because it's the same current passing through this resistor and the linear resistor. 4 IR plus VR minus 6, okay, must equal 0. Now, assuming that VR will turn out to be positive, we can replace IR with 1 over 4 VR squared. 4 VR squared over 4 plus VR minus 6 equals 0. That's VR squared plus VR minus 6 equals 0. And this quadratic equation, or the quadratic right hand side, can be written as VR plus 3 times VR minus 2. So it produces 2 real answers. One of them is at 2 volts, the other is at minus 3 volts. Note that minus 3 volts cannot be the answer, because to be able to obtain that equation, we replace IR with VR squared over 4. And that replacement is valid only for positive VR. Hence, VR equals minus 3 cannot be the answer. The answer must be VR equals 2 volts. And once we have VR equals 2 volts, the corresponding current can be computed from the thermal equation. So we have VR equals 2 volts because VR is positive, and IR equals 1 amp. Okay, I plug in VR equals 2 here, and IR is 1 amp. Okay, so that was step 2. If we were asked the operating point for the nonlinear element, then that would be where we would start. But we're not asked for this current or this voltage, we're asked for something else. The voltage, of course, in terms of this 12 ohm resistor. And that information is hidden in this new topology. So therefore we have to go back to the original circuit in order to figure out this voltage. And that will be our last step, step 3. Okay, substitute the nonlinear resistor with the voltage source Vs equals 2 volt, or a constant current source that provides current that equals to operating point current of the nonlinear element, which is 1 amp. The current source Is equals 1 amp. And solve for V. Well, depending on the situation, one choice might result in a simpler circuit than the other. Okay. And let's, for our case, go with the voltage source replacement alternative. Okay. 8 ohm, 6 ohm, 4 ohms, 7.2 volts, 12 ohms. and we're interested in this voltage here, V. Now here, this is where we had our nonlinear component, and now we know its operating point. It operates at 2 volts and 1 amp. And substitution theorem allows us to replace it with an independent source. Okay, let's use an independent voltage source. Polarity plus minus, and here the polarity is plus minus, the same polarity. Therefore, the voltage that will be given by this voltage source must equal the voltage of the nonlinear resistor. Okay, therefore we have to put here 2 volts. Note that after this substitution, the circuit now becomes completely linear. We have no nonlinear component whatsoever. Therefore, to solve for this voltage, you can apply your favorite method, mesh analysis, nodal analysis, or something else, and you reach the answer. Okay. So let's use node analysis because it seems a reasonable choice for this particular case. We have just a single unknown node voltage, and let's call it E. And that node voltage is no other than the voltage that we're looking for, the voltage of the 12 ohm resistor. Let's write the node equation, just a single equation. Okay, here, this current plus that current plus this current must equal 0. And that will give us the equation from which we obtain E. And E is no other than V. E minus 7.2 over 6. Okay, it's this current. Then plus E over 12. It's this current. And finally, we have E minus 2 over 4, which is this current. And by KCL, this sum must equal to 0. Okay. A single unknown, which is E, and from this equation, we figure out that E equals 3.4 volts. Okay. Therefore, voltage of the 12 ohm resistor is 3.4 volts.